Nuts. So wow, first of all, thanks for having me here, for having us here. It's been a wonderful event, and thanks for being so hardy, you know, that you can sit in this fairly cold climate. You know, I came from Finland, and Finland is expected to be a cold place, right? But actually the exhibition center has been way colder than a lot of places I have been. So thanks for that. Let's get started. So I'm going to go through our TimeCard. Now, our TimeCard has a little bit of history. We thought of some of the things many years ago, and then we sort of adapted it when the time application project started up, or at least when we became aware of it. So this is a little bit of a merger in here. And as you'll see, we have split and partitioned between a module and the actual PCI card, and we'll look a little bit at that. And on our card, we have some additional functionality, mainly an Ethernet interface or a number of Ethernet interfaces, and that gives possibilities, of course, for PTP, etc. And then we have something that I'll bring up that, which I think is one of the greatest source of time errors, and that is incorrectly compensated RF cables to antennas. So people who are looking for high accuracy need to be very careful with that, and we have, I think, a fairly neat solution for that. And then I'll go through some assurance and monitoring areas which are very close to our heart and are things that we have focused on quite a lot, and I think are things that are going to have to come into the time application project area. So with that, our TimeCard looks a bit like this. We have a couple of variants. If you saw on the table, we had a somewhat wider front panel with some additional clock IOs, but essentially we have the same GNSS input, we have the same clock IOs, but in addition to that, we have a couple of Ethernet ports. So we have an electrical gigabit Ethernet with power over Ethernet supported, and then we have an SFP slot. And this one, yeah. So if we look down on the card, we see actually that the card splits into sort of a body and a brain, if you want to think of it that way. So the body of the card is the PCI card. It's a full PCI standard slot that takes just the one lane of PCIe. But actually, the core of this is a small module that we call the sync module. And so we sort of consider that using a full PCI card slot is actually quite expensive real estate in a lot of servers. And so we thought, how could we shrink that into a size, into a form factor that can be fitted in without taking up one of these valuable slots. And of course, the good thing about having a big card is you can have a big oscillator. Big oscillator gets you stability. So where you need the stability and you don't have it available by other means, then you might want to have a big oscillator, and then you need the space, you need the card. Other than that, you can use the sync module, and bar holdover performance, you achieve the same end. So the sync module, or mini time card, however you want to call it, that we currently have is based upon M2. It's a 2242. On this, we have we have essentially two SerDes ports on the back, a lot of GPIO. We have 1000 base TX on the front, and then we have the familiar GNSS antenna input and the clock PPS input-output. And we find that this is a fairly standard way to integrate with a number of solutions, and we have this as a standard product. So looking at the sort of enhancements that we have on the card, if we look at a typical Open Compute server, we could put the card as an actual card into a slot. Then we would have the PCIe interface. We would have the GNSS receiver, the oscillator. We would have the time of day ports, the clock I/O, PPS I/O, But in addition to that, we would have full PTP functionality and actually also NTP functionality. So we would have PTP, master, probe, slave, boundary clock, more or less all of the existing profiles and profile translations supported. And the other thing, obviously, to support PTP, you need the Ethernet interfaces, and we have one copper and one fiber interface. If we integrate that as a module, then we have obviously the PCIe, we have the same PTP, NTP functionality, we have the GNSS receiver oscillator. We lose the fiber port and we lose some of the clock IOs. Actually, the clock IOs could be available as some of the GPIOs on the M2. But the core functionality is there, and really the thing that we're currently working on is two areas. One is to provide the standard TAP driver interface that we currently don't have, and the other thing is to develop a PTM implementation for this to achieve higher accuracy across the PCI interface. So whichever one you choose, the advantage of having in a way, the NIC and the GPS or the GNSS on the same physical module, or in our case on the same FPGA, obviously we don't have any offset between the GNSS clock and the PTP clock. So that's a problem that we don't have to solve because it doesn't exist. The Ethernet ports give us quite a nice sync distribution mechanism, and I'll show you one specific application for that using what we call a smart antenna, which takes care of this RF cable calibration issue. So I'm going to go through this step by step because this is one of the things that I've never really understood why there hasn't been more excitement about this. So I'd like to just go through it slowly. So we have an outdoor box. It's a GPS antenna. It's a multiband in this case, so L1, L5. We have L1, L2 as well, but we have inside of this box the antenna, the GNSS receiver, and the grandmaster function. And so what that allows us to do is to use a standard Ethernet copper fiber connection to whatever, but it could very well be the TimeCard, for example. And we run PTP across this interface. And the advantage of this is we don't have to do the RF cable calibration. So we can totally forget about how long is the cable, what types of cables, how many splitters, what are the different branches on the splitter, and add up all of these values. And this, I would dare to say, is probably one of the greatest sources of at least static time error in typical installations. Obviously, this could be in a server environment, and then we would run a boundary clock function. So we would have, of course, PPS is available. We could also run, of course, PTP either out of another Ethernet interface for local Ethernet connectivity, or we could go through the PCIe into the server. So changing topic completely now, this is looking at some areas that the TAP, we as the sort of TAP group should consider how to solve. So the Department of Homeland Security has put forward various layers and expectations for meeting guarantees of resiliency. And these are defined, and I'm not going to spend a lot of time going through them, but this is something that is going to be requested. One of the things that we do as a way of meeting those requirements is a network-wide GNSS monitoring and assurance system. So this is something that we use across all of our products, and we would also use across the time cards. And with this, we collect to central location all of the statistical data of the GNSS receivers. which could in fact also be various third-party receivers, and do a network-wide analysis of this. So it's not just a local analysis, a local decision on the basis of spoofing and jamming, but this is actually benefiting from all of the information from many hundreds of GNSS stations around the country. Another area getting down below the actual GNSS monitoring, down into the actual monitoring of the health of the timing network, is that in order to do real measurements, we need to put in probes. So all of our equipment, including the time card, including the time module, have probes built in. And we use these probes for collecting statistical data, doing comparison between clocks. We can either do it on real clocks, physical clocks, or on PTP. And again, this information is analyzed and can be done at a network level to get a very wide understanding of the health of the synchronization network. So on looking at the enhanced features, we've shown that the time card can be implemented in a very small footprint. We can put Ethernet ports on this, and this enables PTP, and there are a number of good things that come from having Ethernet and PTP. We have the sync distribution without the coax. So we can, the case that we in particular looked at was that of using a external smart antenna, but obviously there are other benefits from being able to connect up high accuracy over Ethernet. And then the GNSS assurance and the sync and PTP network monitoring. And the call to action, actually a few practical things. The footprint of the tap logic to implement the drivers is actually fairly heavy. So when we looked at this, it was 65% of our FPGA would be just doing the interface for tap. But after some discussions with Julian we immediately started to be able to cut things out which are not essential. So for example, 25% of the entire tap implementation is the 4 clock generators. So we can look, and we would like to get some feedback and input and discussion also on what is actually the essential part and what we can safely put as optional. And then another thing that we are very interested in is using our existing M2 module, and we don't have 10 gig available on that. And we would be interested in implementing PTM over a PCIe 1.x environment. And what we see as the benefit of this is that this is a lower cost, lower power solution. And we really don't see the need for having a full 10 gig on this. And again, we'd like to get some help and input, and we'd like to collaborate around this. Then the obvious needs for resiliency and assurance for the GNSS and the PTP. We are very happy to cooperate again and collaborate on that. And again, my closing note is the Ethernet to the antenna is something that we think has been a little bit overlooked. So whether it's our product or someone else's product, but as a concept, we very much think that this is a good concept. So thank you very much, and if there are questions, I'm happy to take some questions.
Thank you, Kenneth. So, questions? So maybe I have a question.
Okay, I'm getting off light.
Yeah. So, like, if it comes to that M.2 module, so like, how far are we? Let's say if we want to have a like the driver for to make it compatible with tap.
We are working on it now. Let's say for evaluation, possibly only some weeks.
Great.
Yeah.
Look forward for that.
Okay. Thanks.
Awesome. Thank you.